Differential and integral operations 8 use the differential operator theorems to evaluate closed surface integral d sigma dot v, where S is the surface of a sphere of radius capital R centered at the origin, and V is, in part A, x e x hat plus y e y hat plus z e z hat, and in part B, x cube e x hat plus y cube e y hat plus z cube e z hat. Part C we will deal with later. Okay, so what is the relevant theorem here? Differential operator theorem. Well, that is Gauss theorem, the volume integral d tau, divergence of vector v is equal to the closed surface integral d sigma dot v, dot product with vector v. Which theorem is this? This is Gauss theorem. So we're going to use this theorem to find the answer to part A and part B. Now, in part A, we have the vector v given to us. Vector v is x e x hat plus y e y hat plus z e z hat. And we can look at the divergence. Divergence of v is partial derivative with respect to x component of v, plus partial derivative with respect to y of y component of v, plus partial derivative with respect to z of z component of v. And if I look at the partial derivatives here, this is 1, this is 1, this is 1. So I will obtain 1 plus 1 plus 1, which is 3. Okay? So the divergence of v d tau integral I'm looking at is basically 3 volume integral d tau, which is the volume of a sphere centered at the origin, radius capital R. The volume is 4/3 pi capital R cube, volume of a sphere. So the 3's will cancel. Therefore, I have my answer. So I find that the closed surface integral d sigma dot v is 4 pi capital R cube. That's the answer to part A. In part B, I have a different vector v. This vector is x cube e x hat plus y cube e y hat plus z cube e z hat. Now I'm going to calculate the divergence of this. Okay, so divergence of v, I take the x component's x derivative, I obtain 3x squared, y component's y derivative, 3y squared, and 3z squared for the z component, which is 3 times x squared plus y squared plus z squared, which is 3r squared. Okay, so in spherical coordinates. Now the volume integral d tau divergence of v is then the volume integral. What is d tau? We can write it as 4 pi r square, the surface integral multiplied by dr, the differential displacement in the radial axis, and we have 3r square for our divergence. So we have an r integral from 0 to capital R, and 4 times 3, 12 pi r to the fourth power dr, and this will give us 12 pi capital R to the fifth power divided by 5, obviously. So here we have used for d tau the small volume element 4 pi r square dr. Therefore, our answer to closed surface integral d sigma dot product with vector b this time is 12 over 5 pi capital R to the fifth power. All right, so we were asked to use an appropriate differential operator theorem to evaluate this integral. The closed surface integral d sigma dot v is the volume integral over the volume closed by the surface, enclosed by the surface, d tau divergence of v. So we have to calculate divergence of these two vectors. X ex hat y ey hat plus z ez hat divergence is x derivative 1, y derivative 1, z derivative 1, 3. So 3 integral v d tau, which is the volume of the sphere, 4 times pi r cubed. So we obtain 4 pi r cubed. And for x cubed, we have 3x squared, y cubed, 3y squared, z cubed, 3z squared, which is 3 times r squared, the radius square, and the radial distance from the origin. And for d tau, we can use 4 pi r squared dr, which is the surface area of a sphere multiplied by the differential displacement on the radial axis. 4 pi r squared dr, divergence of b is 3r squared. This gives us 12 pi r to 4 dr from 0 to capital R, 12 pi capital R to 5 over 5. So that's our answer for part B.